In this video, we briefly discussed the problem 829 in Cheng's text. In this problem, we have three regions. One is referred to as medium 1, another one is medium 2, and another one is medium 3. Medium 1 and medium 3 in this case are air, and medium 2 is a lossless dielectric of thickness D. And the problem tells us to refer to figure 815, which is on page 402, for more information. By looking at that page and by also referring to the statement of the problem, we see the following. In medium 1, the electric field is given by EI0 e to the minus j beta 1z plus ER0 e to the j beta 1z. HY is given by EI0 over eta naught e to the minus j beta 1z minus ER naught over eta naught e to the j beta 1z, and so on. You can see the rest of them. The main thing to notice here is that this first term is the forward traveling field, the electric field of the forward traveling wave. This is the second part is the electric field of the reverse traveling wave. This is the magnetic field of the forward traveling wave in region 1. Sorry about the interruption there. So in region 2, this first part is the electric field of the positive traveling wave in region 2. This is the electric field of the negative traveling wave in region 2. Here's the magnetic field of the positive traveling wave in region 2, and the magnetic field of the negative traveling wave in region 2. And finally, in region 3, since region 3 extends to infinity in the positive z direction, there will not be any negative traveling waves in region 3, so we have only this electric field of the positive traveling wave in region 3 and the magnetic field of the positive traveling wave in region 3. And I think the only thing here that might be any surprise to you at all is these negative signs, but that comes in from the fact that for the magnetic field, it gets changed in direction relative to the electric field when when the direction of propagation of the wave is reversed. And we've discussed this in class in our analysis of Maxwell's equations in the plane wave case. So if we now take these expressions that we have, and we need to remember, let's see, the left boundary is z equals 0, and therefore, since region 2 has a thickness of d, that means that the right boundary will be at z equals d. And so if we use that, then we see that what we need to do in order to find the relationships between the different fields is we need to enforce the boundary conditions at the two interfaces. So when we enforce the boundary conditions at the interface here, this interface z equals 0, the continuity of Ex will give us this equation 1, and continuity of Hy will give us equation 2. Both of those boundary conditions are obtained here at the boundary z equals 0. At the boundary z equals d, we do the same kind of thing. This is our the equation we get by enforcing continuity of the electric field. And number 4 is the equation we get by enforcing continuity of the magnetic field. Now, these 4 equations are really all we need to solve this problem. As I say here, since we want to find ER naught, E2 plus, E2 minus, and ET0 in terms of EI0, let's let ER0 equal alpha EI0, E2 plus equal gamma EI0, E2 minus equal lambda EI0, and ET0 equal theta EI0. This is just to make these equations come out looking simpler. So when we make those substitutions and then cancel out EI0 everywhere that we can, the 4 equations 1, 2, 3, 4 become 1 prime, 2 prime, 3 prime, and 4 prime. Now, these equations look a lot simpler than 1 through 4, but we can make it look even better if we will let A equal e to the j beta 2d and B equal e to the j beta 1d. If we make those 2 substitutions there, then the 4 equations 1 prime, 2 prime, 3 prime, and 4 prime will become 1 double prime, 2 double prime, 3 double prime, and 4 double prime. And you see these equations look quite simple. And so if we put this into matrix form, it looks like that. And then if we use the use MATLAB and the symbolic matrix solver, this is the solution that we get. Now the first line is the value for alpha. The second line is the value for gamma. The third line is the value for lambda. And the fourth line is the value for theta. Okay? Now, obviously, and let me also make the remark that in these expressions here, ET2, as you would probably guess, represents eta 2, ET0 represents eta naught, and I believe that that's just about that. A and B are self-explanatory, so I believe that that's all you need to know. But obviously the difficulty is that these expressions are rather lengthy. Now, if you look at this, one thing I want to point out I skipped that. I will say this. I have not simplified these answers any further at this time. I don't believe that the answers in the book are correct. In fact, I'm quite confident of that. The reason that I say that is the following. Let me go ahead and elaborate on that. I have solved for one of these coefficients. I have solved for alpha using a different technique, and I came up with an expression that was very, very similar to the expression in the book, but there was a difference. It was not quite the same. And so then I began to wonder, well, which one is correct? Of course, there's no guarantee that either my answer or the book's answer is correct, but I wanted to just investigate this further. Now, if you look at the book's answer for ET0, this is the transmitted field in region 3, and you let D equal 0. So if we assume that there was no region 2, well, in that case, then if there was no region 2, then ET0 should simply be EI0. And if you look at the expression in the book, that's not what would happen if D goes to 0. Instead, if D goes to 0, you would have that ET0 is equal to 2 EI0. So it's certain that the book's answer for ET0 is incorrect. And I suspect from other work I've done that the book's answer for ER0 is very close to being correct, but is off by a small factor in the denominator. To be explicit, I believe that the term in the denominator, eta naught eta 2, should be 2 eta naught eta 2. But I have not solved for E2 plus or E2 minus by this other method that I'm hinting at. Now, here in this lecture, we have all four. We have ER0, E2 plus, E2 minus, and ET0. All of them are solved for here, but of course this is an awkward expression. So I'll leave it at that for this time. If I find a way to easily simplify this, I will do so. But this is the approach, or this is one simple approach for solving this problem. Thanks.